Hello, welcome to EEE 117. This is Dr. Stoops, and we're here to talk about three-phase power. This is going to be the last section on the power group, and then we're going to move on to something else afterwards. So this whole entire time, we've been talking about single-phase power for pretty much a month, and I wanted to quickly show where does the single-phase power come from the generator. And more physically, how does it work? By now you notice I emphasize very strongly on physically understanding what's going on, because then all the equations work out better. So a generator is a cylindrical device with coils wrapped on the outer edge. So this long circular part right here, this is called a stator, where you have coils wrapped around it. And inside it, you're going to have a magnet that spins. Okay. So think of this like a toilet paper roll, and inside here you got like a wooden rod that's just spinning, and the wooden rod has a magnet attached to it. So as the magnet spins, when the North Pole hits or gets closer to these coils, it's gonna attract electrons towards the coil. Right? So remember, North will repel positive charge and try to bring in negative charge. So when the magnet is on the north side, it's going to attract electrons here to give it a more negative polarity for the voltage. And when this spins around and the south pole comes up here, then it's going to repel the electrons and bring in positive charge. So that's why you get this sinusoidal waveform for your output voltage. So I try to draw where the coil is. So you have the coil right here. Think of the magnet to where this north is pointing down and the south is pointing up. You're going to attract a lot of positive charge to the south, the negative terminal of the magnet, and you're going to get a positive voltage, right? That's why we have this little sweeping positive voltage. You can see as the magnet spins away, the strength of the voltage gets less and less, to where eventually the magnet is going to spin in a 360-degree motion inside. It's going to be kind of perpendicular to the coil, right? So here you can see there's neither the north nor the south magnet is close to the coil. So then you're not going to get any real voltage. So when it's completely flat, there's an equal amount of propulsion and attraction for electrons. So you can get literally 0 volts across here because there's nothing pulling it. That's why you have the zero crossing right here, this kind of green area. This is where the voltage kind of dips to 0. Eventually, the magnet is going to spin again, typically clockwise, where now the north pole is close to the coil and the south pole is away. So the north pole will attract electrons, and then you'll have your negative cycle of your voltage source. And this is going to repeat over and over again. So every time we have a complete cycle, the magnet spun 360 degrees inside the generator. And it's going to spin forever, and we're going to keep producing this waveform, right? So, and what's the frequency it spins? It's going to spin at 60 hertz because that's what the power system frequency is, okay? Another thing is what spins this magnet is some type of mechanical input. It could be a diesel engine. It could be a water turbine. It could be a steam engine, right? There's a lot of but in the end of the day, it's mechanical motion that turns this generator, and it induces there's an electric field that induces a voltage on the terminal. Okay, so kind of answer the question is what equipment produces single phase power? A generator. How do we induce voltage across a wire? This is the wire right here, the coils. Magnet rotates and pulls or pushes electrons in the nearby coil. Okay. Now, this is just the most basic one coil section. People got smart. Well, let's keep going. So let's improve the power generation and add more phases, because people realize there's a lot more room to put instead of just putting one coil, we could put another one here, we could put another one there. We could get more wires through and get more voltage sources out of a giant piece of metal. That's pretty much what they thought of. So more coils equal more sources and more phases. Okay. What would be an advantage of using a polyphase circuit? Poly means more than one. Multiple sources on one piece of equipment. So a generator, a vast majority of the price is a physical metal in the construction. So once that's paid, let's just slip in more wires and have 2, maybe 3 sources until the whole thing is completely filled with wires. That way we get more bang for our buck. Okay. Another reason I didn't write here, but you should know, you'll hear it later in power theory, is having multiple sources is a good backup in case one goes down, right? If I have three sources and I lose one, I still have two left to power stuff up. And some devices can still run off of two phases, even when a third one gets dumped. Okay. What's the big disadvantage for using polyphase circuit? Obviously, it's more complex. You got more wires to keep track of, more voltages, more current, and now honestly, more things can mess up. So there's always a balance of complexity versus simplicity and the profit and gains you get from being more complex. Okay. So this is why we chose to go with three phases. Three phases is enough complexity, or is simple enough where we can still keep track of things, and it's not worth adding more phases. Because technically we go 4, 5, 6 phases, but there's diminishing returns of getting it, of having more of those. Mainly it's by more wire. Equipment gets more complex, calculations get more complex. So some people 150 years ago thought 3 is enough, and let's go with that. And this is what we have today. We can't just magically add a fourth phase in America. It's going to cost billions and billions of dollars no one wants to pay for. Okay. So how does a three-phase generator work? Well, what can we add to a single phase, a regular generator, to produce 3 voltage sources? Add 2 more coils. So the magnet sweeps 3 coils. So notice we got the original one, L1. Now we put a second and a third one. And now this magnet is sweeping across 3 coils simultaneously. So if you look over here, when the magnet, the south pole is facing north, you're going to have so when the south pole is facing up towards the first coil, you're going to get your peak right here. See, the black wave is the peak. That's L1 peak. As the magnet moves, you're going to have another coil roughly 120 degrees down to the right. Whenever the south magnet hits that point, you're going to have another peak on red. And it's going to go another 120 degrees, and you're going to have another peak on orange whenever the south pole is close to the coil right here. And then you have another peak up here. So in essence, we just added 2 more phases. Now they're all running at 60 hertz, but we have three voltage sources instead of 1 now. Okay. And the same magnet sweeps of all 3 of them. All right. So how do we save money? So what can we do to add generator? We already did that. Add 2 more coils, so the magnet sweeps 3 coils. How do we save money doing this versus 3 separate generators? Because technically you have 3 separate housing. 1 magnet and housing is shared among 3 coils. We save a lot of money. I don't want to spend extra money buying 2 more pieces of metal and casings and plus the room in the warehouse, right? So there's some advantage to keeping everything in 1 big piece of equipment. So honestly, the whole world runs off of 3-phase generators. Okay. Now, what are the magnitudes and phase shift for 3 sources? Because now we have 3, we don't have 1. Well, mechanically, it makes sense to keep each coil equally distanced apart from each other so everything runs smoothly. If everything noticed in nature and a lot of equipment, symmetry goes a long way in balancing things. Okay, so there's 360 degrees in the entire metal housing. Okay, if we put coil 1 at 0 degrees, let's put the other 2 coils equally apart. So no coil is closer than the others. And by doing this, each one is 120 degrees apart. So we have the smoothest transition. So as the magnet spins, no one coil has more precedence over the next one. They're equally spaced apart. It's equality for all. That's what we're going for. That inherently makes things more stable from a mechanical standpoint. There's less friction. There's less things tugging the rotor and making vibrations. And from an electrical standpoint, all the waveforms are exactly 120 degrees apart. So each peak from the first phase to the second to the third, they're all 120 degrees apart. And why is it 120 degrees? Because the coils are physically displaced 120 degrees apart. Okay. If we had 4 phases, this would be 90 degrees apart. If we had 2 phases, this would be 180 degrees apart. You see? So it's just whatever phases get put into 360 degrees worth of rotation, that's the balance between them. Okay. What are the magnitudes, right? Is any one coil stronger than the other one? No, because we're going to make sure the coils have equal amount of winding and equal amount of coils. So no one coil is going to be stronger than the other. so that there's no unbalance. Because if one coil is stronger than the other, the magnet will pull harder to one and there'll be a physical unbalance in the generator. So it's going to be like kind of shimmying around. Think of like a washing machine that's unbalanced. You hear is knocking all the time whenever you're running it. That's a death sentence for a generator because it's going to mechanically tear itself apart. So equal amount of magnitude. So all voltage sources have the exact same output. They're all 120 degrees apart. That's physically how the voltage source will operate in a generator. Okay. So what are the magnitudes of all three phases relative to each other? Since there's only one magnet and the coils are equally wound, the magnitudes are all the same value. What are the phase shifts between all three phases? They're all 120 degrees apart. Three coils equally placed around a circle, 360 degrees divided by three coils is 120 degree separation. Okay, so that's where you've heard three-phase power is 120 degrees apart. This is where it came from. Okay, it's physically how it's built inside the generator. So we don't want to sit there and draw that circular generator every time. That's a lot of work. So what I'm doing is we just draw a black box, calls it a three-phase voltage source, and it's going to have three wires. Okay, so because remember, we get three sources now, right? So we're going to have three wires. Wire for source one, wire for source two, wire for source three. Loadings, each load will be a three-phase load, which will have three terminals. One for wire one for wire two, one for wire three. Okay, so that's a three-phase loading. How many voltage terminal nodes do we need for a three-phase source? Three voltage sources. How many lines do we need? Three lines. How many loads do we need? We need three loads. So internal to here, there's going to be three separate loads. Or it's going to be one big load that has three equal loading on these terminals. Okay. So this is kind of how a three-phase circuit or three-phase system is being built up from the ground. So this is why you ever look overhead in your power lines. It's not a single wire. It's always multiple wires. It's like 3 or 4 wires typically, right? 3 wires is all 3 main lines. You might have a 4th wire as a ground wire or a return wire as a safety, just in case type of thing. So let's go ahead and officially name these 3 voltages. We're going to name the first one VA, the second one VB, and second one VC. So I'm sure you've heard before, if 3-phase voltage is A, B, and C. So VA, VB, VC. Okay. Quantify them is going to be Vm cosine of omega t plus 0 degrees. So VA is always at a 0 degrees. VB is going to be the same magnitude Vm as VA. Cosine omega t, so they're both sharing the same frequency, 60 hertz, technically 377 radians per second. But we're going to have a negative 120 degree phase shift because remember, look, it comes later. So remember, if this is time equals 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, right? VA will hit about 1.2 seconds right here. That's where it maxes out. VB is going to hit 1, 2, 3, 3.5 seconds later. So you can see just as you clock set time of one Mississippi, 2 Mississippi, 3 Mississippi, A comes first on the peak, B comes second, C comes third. So you know B phase is lagging or it's behind by 120 degrees. So we put negative 120 degrees because it's behind. Okay. VC is going to be another 3.5 seconds past VB. So it's going to be another 120 degrees behind. So it's going to be a negative 240 degrees. Okay. A lot of programs will actually reference when it crosses over the 0 crossing rather than the peak because it's easier to detect whenever something from a programming standpoint or a measurement standpoint, it's easier to detect when something goes negative to positive and flips over. So anytime the signal flips over from negative to positive, we could timestamp that. So VA is 0 degrees. Notice right here, it flips from negative to positive. So it's 120 here. It flips from negative to positive over here. It's 240 here. So that's how you see your time delay. Okay, so the big thing here, look at the magnitudes are all the same, but look at the phase shift. 0 degrees, negative 120, negative 240. That's that 120 degree separation we were talking about before. Okay. All right. We could do a phasor representation of this circuit, where phasor-wise we could have VA, which is on the x-axis. So that's 0 degrees right here. So that's VA. VB, using phasors, could be VM, phase angle, negative 120 degrees, or phasor, negative 120 degrees. So from a graphical standpoint, you draw a phasor, negative 120 means we go from 0 and go downwards 120 degrees, so about right here. So it's going to be down and to the left. This is about 120 degree separation. VC is going to be VM angle negative 240. So you could take the VB, which is negative 120, put another negative 120 here. So you're going to go be up and to the left. This is VC vector. Now, a lot of people will draw VC as positive 120 degrees instead, because you can always go from 0 degrees and go the other way and add degrees. Another thing to think of is, remember, you can always add or subtract 360 degrees from any angle. So you add 360 degrees, it'll be positive 120. So negative 240 and positive 120 are literally the same angle on your graph, your phasors. Okay. But the big thing is this equal 3y. It's like the Mercedes-Benz emblem. It's 3y, it's 3 vectors equally distant 120 degrees apart with the same magnitude. Okay. That's how you represent a balanced three-phase source. This is physically what's going on with the actual waveform, but a lot of people like to draw vectors because it's easier to read than a graph with cosine and sine functions. Okay. So here, kind of rehashing what I talked about for a balanced three-phase positive sequence system, right? Positive sequence means VA comes first and then VB and VC. So if we sit on the side right here and watch the whole vector term. So at 60 hertz, think about the Mercedes-Benz symbol, put it on the ground on your desk and spin it. Spin it like a spinner or a top. Okay. As it spins, it's going to go clockwise. So as we're sitting on the edge of the table, we're going to see VA sweep across us. So that's going to come first. And then VB will sweep into our eyesight. That'll be B phase. And then C phase will sweep into our eyesight, and that'll be C phase. So as this rotates counterclockwise, that's an orientation. I always see A first, A fly by, then B fly by, and then C fly by. That's what a positive sequence system means. It's called rotation right here. A happens, then B happens, and C phase. And so it's A, B, C rotation. We already talked all the magnitudes of the vectors. The tip right here of the arrows are all the same. Everything is 120 degrees apart. Okay. The other thing, the frequency, the whole circuit is spinning at 60 hertz. So that means all these vectors are all spinning at the same speed. No one's going faster than the other. Otherwise, the vectors will eventually go closer to each other and overtake each other. That's not going to happen. Everything's locked at 60 hertz. Why is it locked at 60 hertz? You remember, this is one generator. Those coils aren't moving. They're always going to be 120 degrees apart. So as long as those coils physically aren't moving, this is all going to be rotating in the same angle. Okay. So USA has 60 hertz. EU, Europe has 50 hertz. Okay. So this is what a balanced three-phase positive sequence system is going to look like. Okay. Now, we could draw this from a circuit modeling standpoint. We won't go into detail and see, because if you want to literally sit there and say, I want laws of node analysis, KVL, right, Ohm's law, all that. If you want to do that hard circuit analysis, we could break it down into individual components. A three-phase source is going to be 3 separate voltage sources, VA, VB, VC, and there's going to be a neutral point you connect the negative terminals to, and each one's going to branch out A phase, B phase, and C phase. Okay. So A is the A phase terminal. So you'll expect this to be the node that you connect the rest of your system to for A phase, B phase, and C phase. Now, on the right-hand side, this is the same circuit, except we have some internal impedance and reactance built into the generator. The left-hand side is an ideal one where everything's perfect. We're not taking into internal losses. Realistically, a generator has a giant coil of wire to power it. But guess what a giant coil of wire is? It's also a giant inductor. So you're going to have to put this inductance to represent the impedance of the main coils powering the generator. You also, because there's a lot of wires, you got thousands of feet of wire inside a generator, right? The 1,000+ feet of wire will eventually add up. You'll have some internal resistance in the generator too. So if I want to be really, really real life accurate to the 10th degree, you will have to put your resistance and inductance in series with your voltage source to represent a physical generator. Okay. Unless you're going to be the generator manufacturer or you're doing some extremely advanced power system analysis, most people don't write this in. They use a left-hand model. But I want to cheat you out. If you ever see this, don't be shocked that it's like this is wrong, blah, blah, blah. This is a technically correct one if you're going to that much detail. So your A phase and B phase, C phase terminals will be past these impedances. Because these A, B, and C phase terminals represent the physical terminals in a generator. If I purchase a generator, on the side of the generator, there's going to be a patch panel, and there's going to be 4 or 6 iron slugs. And you're going to attach your wires to those. 2 iron slugs are going to be VA positive, VA negative. And another 2 iron slugs are for VB positive and negative and C positive and negative. Okay. So you're just going to clamp on your main wire to it, and then you're going to have your voltage source. But on that side connection panel, this R and JX are already built into the generator. We can't separate it. Okay. The fourth part, so you have A, B, and C. And the fourth thing to note, there's a neutral here. So it's very important to note when you buy generators, this neutral is something you have to wire up. It's not internal to some generators, it might be internal, but most big generators, it's not internal. You're going to have to wire it up. Okay. It's all flickering. Let me make sure we're still sharing the right thing. Okay. So this is just what a voltage source, a 3-phase voltage source will look like on when you're doing circuit analysis. Okay. So let's calculate the voltages for a 3-phase voltage source. This gets a little different now because, these values can change based on your system. So for example, this particular system, if I know VA is 7.2 kV, and we're going to say RMS values. I didn't say previously because we're using sines and cosines, but now we're going to stick to RMS values. If I measure 7.2 angle 0 degrees for my VRMS, right? I already know what VB and VC are. By rules, if it's a balanced 3-phase system, positive sequence, so balanced positive sequence 3-phase system, VB is going to be the same magnitude, It's going to be the same magnitude, 7.2 kV, angle negative 120 degrees. VC is going to be the same, 7.2 kV, angle positive 120 degrees. And the whole reason I know this is because of that balanced system. All magnitudes must be equal. B and C phase are 120 degrees and positive 120 degrees apart. Right? So in my mind, I literally memorized to the point where if I ever see VA, VB, VC, I just write the same number for all VA, the magnitudes, go down the column for the same numbers. VB is 0 degrees, VA 0 degrees, VB negative 120, VC positive 120. Okay, that's for your standard balance system. All right, I'm saying that 1,000 times because I want to hammer it in. This is the bread and butter of any 3-phase system. Okay. Excuse me. All right, so now we have the voltage source. Let's see what a 3-phase load looks like. So notice we have the A, B, and C source. We got a wire going to the load. You have IA, IB, and IC. So you have 3-phase current. And then you got a load that's ZA, ZB, and ZC. So all the loads are connected from B phase to a neutral point. Okay. So there's 3 loads the sources connects to a 3-phase load as well. What are the load characteristics? You have 3 loads in a balanced system. ZA, ZB, and ZC must all be equal. So these are 3 identical loads. So think of like if you have a heater for your industrial center, all 3 of these must be the exact same heater. Otherwise, it's not going to be balanced anymore. If one of these are bigger than the other, your system is going to be all out of balance, and all those rules we talked about won't apply anymore. You're going to do everything manual. It's going to suck. So 90% of the time in all power systems, we assume that all these are balanced. Okay. Now notice they also have 2 terminals each. You have a positive and negative. So the standard play is the positive terminal goes to the A, B, and C phase respectively. And then the negative terminals we tie together into a neutral point. The thing is we can't leave the wire floating. It has to have a return path, right? So for example, if A phase is hot, if A phase is the maximum right now, you're gonna have current flowing at A phase. B and C phase, the voltages will be negative for that instance in time. So A phase current will flow out to the neutral, and it'll flow, and then current will flow out to B phase and out to C phase and return back to the source. Because you remember that 3-phase vector, right? So not even though the currents are all drawn pointing in one direction, there are times when these are negative and these are positive. Because remember, AC systems, right? You have a positive peak and a negative peak. Each source has a positive peak and negative peak. At any instance in time, one or two of these sources are positive and the other one is negative, right? So if A phase is positive, more likely B and C phase are negative, so current will flow out of A phase and go back into B and C phase. If B and C phase are both positive, then current will flow out of B and C phase, and A phase is definitely negative, and they'll both flow back into A phase being negative. So it's kind of like a back and forth push between three current source or voltage sources. Okay. Now, how do we calculate the ohms? How do we calculate current going through a circuit? If I know the voltage, I know the impedance. The beauty of a balanced system is they're all going to be very similar. IA equals VA over ZA. IB equals VB over ZB. IC equals VC over ZC, right? V voltage of C phase over impedance of C phase. Kind of hard to say that. Okay. And honestly, the nice beauty about this kind of shows right here is if I calculate A phase, so typically we have to manually calculate A phase. And I know my IRMS quantities in a balanced system, IRMS could be a 0 degrees for A phase. I already know B and C phase. Just the same rules for voltages apply for currents. If I know A phase, B and C phase are going to be the exact same magnitude, and their phase angles be negative 120 degrees apart. So B phase is negative 120, C phase is positive 120 degrees. Okay, so this is an ideal condition. Right? And so whatever this main number is, all the magnitudes are the same, and you're just adding and subtracting 120 degrees. Now, I wrote 0 degrees here. In real life, this could be positive 30 degrees. If this is positive 30 degrees, then you'll take 30 and you're just going to add 30 degrees here and add 30 degrees there as well. So even though one angle might be not beside, if A phase is non-zero, B and C phase will still be that negative 120, positive 120. You just add it in. Okay, so let's say I calculate everything and this is angle 10 degrees. If this is angle positive 10 degrees, IB will be negative 120 plus 10 degrees, so it'll be negative 110. IC will be plus 120 plus 10 will be positive 130 degrees. Okay. When we do some calculations, you'll see it come out. Okay. So here, let's go try to calculate A, B, and C phase, or calculate three-phase voltages and currents. So let's say we have a system. I give you VA is 7 kV angle 0 degrees, right? And I told you before, I say again, just assume everything from here on out is RMS values. I gave you VA. I also tell you the impedance for all three of this is 20 angle 30 degrees ohms per phase. So all three of these are Z equals 20 angle 30 degrees ohms. You assume a 60 hertz system. We have three phase, positive sequence, and we should assume a balance as well. Okay. I already know B and C phase. Remember our rules. If this is 7 angle 0 degrees, VB is 7.0 angle negative 120 degrees kV. VC is 7.0 angle positive 120 kV. Right? So it's just a balanced system, makes life a lot easier. Okay. Now let's go ahead and calculate IA. IA is going to be, because if you literally take the voltage at A phase, put it all the way to the load, because there's nothing in between. This is the same node. So your voltage from A to neutral we assume 0 volts for any balanced system. It's 0 volts here, it's 0 volts here. So my voltage is literally 7.0 angle 0 degrees kV. My impedance is 20 angle 30 degrees. I number crunch this. My current is 350 amps angle negative 30 degrees. So that's my A phase current. Notice is not, I always write 0 degrees for A phase, but realistically, we might be off a little bit. In this case, we're negative 30 degrees. Remember the rule. B and C phase are literally going to be the same magnitude. So if A phase is 350, B phase, let's write 350, C phase, let's write 350. Take that negative 30 degrees, bring us with us, and subtract them. So for B phase, negative 30 degrees comes with us from A phase. We subtract another 120 degrees, so we get negative 150 degrees. Okay. C phase, same thing, bring the negative 30 degrees with us, we subtract 240 degrees, right? And we get negative 270 degrees. So if you compare all three currents, notice that magnitudes are still equal, 350, 350, 350. But the phase angles have that negative 120 degree phase shift. Negative 30 subtract 120 is negative 150. Negative 150 subtract, negative 150 subtract 120, you get negative 270. Or we could swap it around and say, instead of negative 240 degrees, we add positive 120 degrees and say this is positive 90 degrees. So negative 120 degrees and positive 90 degrees are the same exact number for angles. Okay. So notice that it's still a balanced system, even though the phase angles are all shifted a little bit. That's perfectly fine and legal. Okay. So this is how you look at a three-phase system. Now, the real work I had to do was only on A phase. I only had to do my circuit analysis in A phase. I knew B and C phase immediately because of the balance properties. And we're just doing that number crunching of adding and subtracting 120 degrees. Okay. And this is the beauty for a three-phase system. Now, let's draw this on a phasor diagram. So remember, VA is at 0 degrees. So you have 0 degrees. So it's on a x-axis. And it's pretty far out. This is some kV. Notice VB down here. This is negative 120 degrees off. So it's down and to the left. You got VC up and to the left, a negative 120 degrees as well, right? So VA, B, and C are perfectly 120 degrees apart, and they're same magnitudes. Now look at IA. We say IA was 350, so it's a shorter. Now this is a little drawn out scale, but this is a smaller phase vector. And notice that negative 30 degrees. You see how we're off by 30 degrees from A phase? That's a negative 30 degree phase shift on the current. Notice B phase is negative 30 degrees off from the voltage on B phase, and has a smaller magnitude than VB. IA and IB both have the same magnitude. They're just shifted off negative 30 degrees from their B phase their voltage equivalent for that phase. C phase, same as well. We're negative 130 degrees off, and we're going up straight to page. This is either positive 90 degrees or negative 270 degrees. Okay, sorry. Okay. Now, if you compare IA, IB, and IC, there will be 120 degrees apart as well, right? The whole thing is just shifted over by 30 degrees. That's it. Okay, so I just want to show you when you actually do circuit analysis, your vectors might shift a little bit, right? But in the end of the day, they should still all be this, like, I call it the Mercedes-Benz emblem. If you ever know cars, right? It's 3 points in a circle. Think of that, just shifted up. You're shifting it on the page a little bit. Okay. So this is where we take a break, and I want you to do a three-phase circuit problem. We have the same system, except your VA is 2.4 kV, angle 0 degrees. You assume RMS values. Your Z impedance is 6 angle positive 45 degrees for all three phases, ZA, ZB, and ZC. You have balanced three-phase positive sequence at 60 hertz. I want you to calculate IA, just like what we did before. Calculate IB and calculate IC. I'll leave that up to you. And I want you to draw your three-phase vectors right here as well. Okay. It looks similar, but they'll be a little bit different because this is a 45-degree phase shift and the numbers are a little off. They're not the same numbers before. Okay, so let's take our 15-20-minute break, and we'll come back in a little bit, and we'll see what your answers look like. So see you in a little bit. All right, hello, welcome back to EEE 117. We're going to pick up where we left off with this three-phase circuit problem. So let's go ahead and see how we did it. So first thing is you already got VA and you got Z for all three phases. So it's just simple. Current is just Ohm's law, VA over ZA, and you get 400 angle negative 45 degrees amps. All right. IB and IC can easily be solved because you literally just, it's the same magnitude because it's a balanced three-phase system, positive sequence. So use 400, 400, 400, and just make sure you subtract 120 degrees between A and B. And then you could subtract another 120 degrees between B and C, or you just add 120 degrees between A and C. Either one works. At the end of the day, phase angles for A is negative 45 degrees. Phase angle of B is negative 165 degrees, which is negative 120 minus 45. and IC is positive 75 degrees, which is positive 120 degrees minus 45 degrees, right? So here's your balance current, and that's what's flowing into the load from the system. Then we go ahead and draw all the magnitudes out. So here you have IA, IB, and IC, again, 120 degrees apart, right? About should be 2.54 kV in length. IA, B, and C, this is 400 amps in length with a negative 45-degree phase shift from the respective voltage, right? Additionally, if you look, you can see IA, IB, and IC are all 120 degrees apart as well, right? So this again, typically you draw these phasor magnitudes, you'll notice that they should be very symmetrical looking unless you have an unbalanced system, okay? So we could keep on going with the three-phase system. In this time, normally we had a neutral that was not wired, but now we put a wired neutral in. This is typically for one, if you have single phase loads that unbalance the system, you're going to want to have a neutral wire because you're going to have neutral current flowing through it. Now in a balanced system, both neutral points are dead 0 volts, so you shouldn't have any issues. But a couple rules to note that at any point in time, if you add 3 voltages together, VA, VB, and VC, that should equal 0. That's a conservation of energy, right? Basically, think about in generators, north magnet and south magnet. So there's an equal amount of negative voltage from the south magnet and a corresponding equal amount of positive, there's an equal amount of positive voltage coming from the magnet when the south terminal is nearby. At the same time, there's an equal amount of negative voltage when the north terminal is nearby as well, right? So because the magnet has a conservation of energy, naturally these voltages will have a same conservation as well, because you can't just create voltage out in there. It comes from a magnet for a generator. So if you ever add all 3 of these instantaneously, they should all equal to 0, right? At a neutral point here, since all the voltages are balanced, if you ever try to add all 3 voltages, you're going to naturally get 0 as well vectorially. So at a neutral point in a balanced system, this is 0 volts at all times. Okay, that's why typically neutral, 90% of the time for neutral, you expect 0 volts when you do your calculations. I don't see why it would ever change unless you have a unbalanced system, which we don't cover in this class right now because it's a little complicated. And later in your on college career, you'll look into it. Okay, but just to note that there is a neutral wire typically in place, especially in industrial settings where you might have, because one of these might be 3 separate lights or 3 separate rooms. You could turn one off, so you're gonna have to have, because it's unbalanced, and you're gonna have to have a path for the current to flow whenever you turn some of your loads on and off. Okay. Now for current in a balanced system, you technically should have no current flowing through the neutral. Again, with current, same thing, a conservation energy. If you add up I1, I2, I3 vectorially, you should equal to 0. The neutral point is literally KVL, where you're taking all, or KCL, where you're taking all your currents going into neutral. They should all add up to 0. Another way I have to think about it, if current B pushes in, current C pushes in, current A pushes in, you add them all together, that should be what comes out of the neutral point here. Again, if it balances, it should be 0 vectorial. You can add all your vectors, and then you should have 0 current as well. Okay. So, but we do label IN here in case it is unbalanced. And the way a lot of engineering books and people label it, IN is in the same direction as IA, IB, and IC. So they're all pointing from left to right or from source to load, right? So if you add all these up together, there should be 0. If they're not 0, you have to all add them up together, and then you'll get a non-zero number for the neutral current. Okay. Now, all this time we've been talking about connecting loads and sources together, mainly with this IBIC and the neutral kind of bonded together in the middle. Formally, this is called a Y-connected configuration, where it kind of makes an inverted Y. You see like the main stalk here and the 2 points coming out for the Y. So we call this a Y-connected voltage source, right? And the main thing to drive here is the neutral, all the negative terminals of the generator each source should all come together to a bonded neutral point, and that neutral point should be 0 volts. Okay. Coming out of the generator, you have IA, IB, and IC. So this is a Y-connected voltage source. Okay. You do have a delta connected voltage source. This is pretty rare, but it can technically happen because no one says you can't just take both the sources and kind of connect them back to back like this. So you see VA, the positive terminal of VA is connected to A phase, which is also connected to negative terminal of C phase, and you kind of daisy chain it around. It's called delta because you literally make a triangle here. Okay, so this is formally called a delta connection where positive A is connected to negative C, positive C is connected to negative B, positive B is connected to negative A. It kind of makes like this little, the way I see it, they're kind of like pointing into each other in a triangle fashion. Now, at each corner of the triangle, you could draw out a current and call this A phase, B phase, and C phase, IA, IB, IC. Okay, one big difference from a Y-connected voltage source is there is no neutral. So in a delta connected system, by definition, there is no neutral point because nowhere in this circle or this triangle are we summing up all three currents to 0 or all three voltages to 0. Every point, A, B, C, is only interacting with 2 voltage sources. So all these points will be non-zero numbers. Okay. So Y-connected load source, very common. Delta connected source, very uncommon, but they are out there for other reasons. Okay. So just wanted to give you the basics on Y-connected load. So loads, we had the same idea. We got Y-connected loads where you have three separate resistors or 3 separate loads. They come together. So their positive terminals going into the load are from A, B, C. Those are the lines from the power system coming into the load, like so. The negative terminals of all the loads are all going to be bonded together in one node called a neutral point, right? And if they're balanced, this neutral point should be 0 volts. This is formally called a Y-connected load, right? There is a neutral here at the center of the Y-connected load, and this is 0 volts as well. Notice you have current IA, IB, IC coming in. They're both going to each individual load. Lastly, you have something called a delta connected load. So they kind of draw this as a rectangle, but if you think about just bending this AB a little bit sideways like this, ZC a little bit sideways like this, you could kind of see the delta connection, right? They stretch it out to make it a little box shape just because it's more neater, I would suppose, right? This is formally a delta connected load. These are out there. They're pretty rare. One of the big reasons why you don't use a delta connected load is there is no neutral. So you can't run single phase loads on this. And without having a neutral, you have some issues on safety and what would happen if one of these go bad and whatnot. So they do exist more in the high voltage class and the low voltage levels or medium voltage levels in industrial plants. You almost never see delta connected loads because it's a little more dangerous. The one big advantage of running a delta connected load is you could take your load is between 2 phases rather than just a phase and a neutral like the Y connected load. So by going from phase to phase, you can actually get higher voltage for the same system as a Y connected load. So that's one of the big advantages using delta load is your voltage this is new voltage VAB, so voltage between A phase and B phase is going to be higher than up here, which is just the voltage of A to 0. Okay. Notice that we have no neutral, it's not present because there is no central point to cancel all the voltages and current out. So we just don't have it. Okay. And another big difference is the current come in at IA, IB, and IC. They don't go to each individual load. If you notice IA comes in, it gets split going down one resistor or one impedance and another. So current kind of branches out into the delta. It gets a little more complicated on the calculation side. Okay. So that's the 4 types. Y-connect, well, it's really 2 classes, Y-connected things and delta connected things, where you have a Y-connected source and a delta connected source and a Y-connected load and a delta connected load. So a lot of people ask, well, which one's better? On the source side, typically Y sources are more common in the world. The main reason why is we want to have a neutral point that we could then ground for safety issues, and then for detecting abnormal states. So a neutral is actually very helpful and useful in power system analysis. So anytime we have a neutral, anytime we can, we will build a neutral in a generation site. Okay. Now, the question is remember, all generators are the same. When you have a generator, remember I said you have 6 terminals. So a generator itself only gives you positive VA, negative VA, positive VC, negative VC, positive VB, negative VB, right? The generator itself does not pre-come wired via delta. So all these points of these wires connection, this is what you do it externally through literally cables. So when you buy a generator and install it, it is not a Y or delta connected generator. You configure it with literally installing wires and bus bar everywhere. And so that's kind of your design, right? So if for some reason you really don't need a Y connected source, you can go rewire the terminal as a generator to be delta on site. It's not that complicated. But I would say you have to give me a good reason why you want to do this. Okay. So that's the end of the day, source Y connected generators tend to be way more popular than delta connected generators. Okay. What about loads? Which one's better, delta or Y? Again, typically Y connected loads are a lot more prevalent in the power system. Right. Not only is the delta connected more complicated in analysis, there's no safety feature because you don't have a neutral grounded anywhere. And delta is harder for delta loads to support unbalanced, single phase loads, right? Typically single phase loads, you use a Y connected load configuration. Okay, so Y more popular for smaller loads. But if you have a very, very large motor, a very, very big device, it could be useful to do delta connection, mainly because you could get a higher voltage across each load, which could give you more power. So, don't be shy. Don't be surprised if you see a delta connected load that's extremely high powered because they just wanted to cheap out a little bit and get a little free extra voltage. Because typically VAB will be a higher voltage than VA to N right here on this Y connected load. That's the main advantage of the delta connection. Okay. Now, again, for circuit analysis, typically, if we ever see a delta load, you've probably seen a delta connected resistor set in Engineering 17. It's more advantageous to literally convert this to a Y load and then do our analysis. Analysis on a Y load is very easy. You just figure A phase and B and C phase follow suit. Delta connected load, it gets a little harder because you got to figure out the current flowing through here, and there's extra steps in calculations, right? So very common is anytime you have a delta load connected to a Y load to make your circuit analysis easier. Now, again, you learn how to do a Y to delta conversion in Engineering 17 with those resistors. Those are really long, drawn out equations, but if all these impedances, ZA, ZB, and CV, ZC are all the same numbers, Z delta will be the same numbers as well. And the only difference between these two is just you divide by 3. Okay. So ZY, so if I have Z delta, let's say I have delta right here, I want to convert to Y. I literally take whatever this number is, divide by 3, and replace it with redraw it as a Y connected load with this ZA as a ZY. So ZA, ZB, ZC, all ZYs. 1, 2, 3. Okay. Very, very simple. Most people end up doing this for analysis and calculations. Okay. Kind of a little thing I remember is the delta connection is always wider than the Y connection. Because if you look at the bottom, delta is a Y base, Y is a very tiny, thin base. So every time you look at impedances, the Z delta should always be 3 times higher than the ZY. Okay, so just remember, a delta is a bigger triangle and Y is a smaller like configuration. And then impedance will follow suit as well. Okay. Other people like to draw the delta, and you can technically draw the Y inside the triangle. Just remember which one's bigger and smaller. Okay. So kind of show some example, maybe it's not examples, but let's see it all in action. So anytime you have a configuration, You should always ask yourself, is this delta or Y connected? One of the main, again, the easiest way to see is there neutral or not? A generator connected here, you see neutral and you see a fourth wire, that's a very telltale sign you have a Y connected source. On the load side, notice you have A, B, and C coming in. They all bind together at a neutral with a wire coming out. This is a Y connected load as well. So this is a Y source, Y load connection system. Okay, what about over here? Let's get a little more complicated. Let's put some circuits in. Is this Y or delta? Well, look on the left side. You see you have three generators, three sources, three impedances coming out, A, B, and C. But again, notice the negative terminals, telltale sign, they're all bonding together to neutral. Even though we don't have the wire coming out, this is still a Y-connected source. Now on the load side, notice that you have one impedance. They're all the same impedance, so you know it's balanced, but they're going between A and B, B and C, and C and A, and there's no neutral present. So this is a kind of telltale sign that this is a delta-connected load. So this is a Y-delta system. What about this one? Okay, now we're getting a little more complicated. We're adding up things in the middle. So we have three things this time. We have VA, VB, VC, so we have a source. We got a capacitor bank in the middle. And then we got a load. So first off, let's look at the source. Again, telltale sign, there's a neutral right here, so this must be a Y-connected load. Now look at the cap bank. Which one is this? It's kind of a little hard to see, but look at the capacitor. Just figure out where are 2 points. This capacitor is connected A to B. The second capacitor is connected to B to C. The third capacitor is connected C to A. There is no neutral here, and each devices are connected between phases, so we can surmise this is a delta connected load. Now, this doesn't look anything like a delta on paper, but just from looking at terminals, we can know it's a delta connected load. And then the last question is, what about the actual load itself? Is it delta to Y? Now, it's kind of a trick question. You don't know what's in this box. You don't know the configuration, do you? It doesn't tell you either. So the load is not sure. We don't know. It's a mystery. They should have told us Y or delta connected somewhere. And in real life, you should know if this is Y delta. So this is kind of a little, maybe they didn't need it to do this circuit analysis, but they really should have said, hey, this is a Y or delta connected load, in case you want to open up the box and go inside, right? Now, if I was going to have to guess, I would most likely guess this is a Y connected load because they're more common. But I can't 100% say that. It's unknown. Okay. So that's kind of a summary of the three-phase systems. Wanted to touch on a little basics here and there. So most of the power system is a three-phase balanced ABC rotation system, where voltages are VA equals the VM angle 0 degrees. VB is the same VM angle negative 120 degrees. VC is the same VM angle positive 120 degrees. Same magnitude, 120 degree separation of phases. Current, same thing, IA, IB, IC, IA is an IM, you calculate this, you get an angle. Now you'll have a theta, this is typically a phase shift. So current typically, most likely your current has a different phase shift than your voltage. A lot of times the voltage, 0 degrees for VA is a reference we start at just to make the numbers easy. But this phase angle IA could be like 45 degrees. It'll be 32 degrees or negative 15, right? This really depends on your load. So there will most likely be a phase shift here. For A phase, you just add the phase angle 0 degrees, so there's no change. VB is going to be the same magnitude as IA, except you're going to have that phase shift and you're going to add a negative 120 degrees. VC is going to have the same IM and you're going to have that current phase shift plus 120 degrees. And then you might have a neutral sometimes, and that's going to be 0 amps for a balanced system. You could draw a vector VA, VBC that are equally distant, 120 degrees apart, and the arrows are all the same magnitude because it's a balanced system. Okay, here you have a voltage source that's either delta connected or Y connected, where Y connected, this one right here, is a more common one. Loads can be either delta or Y, where this is a Y connected load. And again, this is more common. But there are delta connected loads out in the system, so don't be surprised if you see them.
Lastly, anytime you can always do a conversion from a delta load to a Y load, or vice versa. I didn't say up there, but you could deduce. If you have Z delta and you want to go to a Y connected load, do the Z of the delta divided by 3 is the Z of the Y, or the impedance of the Y connected source. So you redraw the circuit, and that's your new impedance. Or if you have a Y connected load and you want to go to a delta connected load for some reason, you multiply the impedance by 3, and you redraw the circuit as a delta connected load. Okay. So that's all I have for today. I hope you was a good introduction for three-phase systems. As long as you know A phase and the system is balanced, it's not that different from a single phase system. Just remember there are two more phases that follow suit. Your delta or Y is the only thing that you really have to take into consideration right now. We'll come back next class period and talk more details about the three-phase systems and other nuances that come with it. Okay, so thanks for showing up. I hope you guys have a good day, and we'll catch you in the